welcome everybody to this second version of this workshop on ultra high frequency gravitational waves. The first one we had it already 2 years ago, and as you know, we had this a white paper that came out after that, and so we can see that with this second one that we organized now with Francesco, Jessica, Nancy, Valerie, and Mike and Sebastian. So I think we have now the second version with I think more than 4 times the number of participants, which looks that shows that there's some interest in the community, and I think we are very much looking forward for this meeting because this subject I think is getting more interest on the community, and we are convinced that it has a lot of future. And for that, it's clear that there's plenty to be done because it's not clear what are the right best roads to follow. And that's I think we will need all the interaction from that we expect from this meeting to see if we have a better idea of what to do next as a community. So starting in this way, so we have the pleasure to have Mike to give us the first introductory talk. And so the floor is yours, Mike.
Okay, thank you. Me share the screen. I hope that's
perfect.
Operational. Good. Well, as Fernando says, welcome everybody from wherever you're logged in. I was going to say good morning or good afternoon, but I don't know how many of those different time zones we're contacting, but it's great to have people online participating in this workshop. So first of all, let's say thank you to the organizers. I've listed them there. I've done a lot of work to prepare this workshop. We should also thank CERN for allowing us to use the meeting software, which let's hope it stays up for the full meeting. I'm sure it will. And also to the Hawking Centre for Theoretical Cosmology in Cambridge for hosting our website, which is shown there. I'll come back to that issue a bit later. Well, I was asked to say something about how we'd actually got here, and so I've labelled this the journey so far. And the journey so far began before the events of 2015. There are many theoretical papers on gravitational wave, electromagnetic wave interactions from the 1960s and 70s, many experimental ideas in the 1970s and for many decades afterwards. And quite a few of those experimental ideas had their operational frequencies really biased into the ultra high frequencies, and so it's interesting to look back on those papers now. Of course, as soon as the propagation properties of gravitational waves were sorted out in an analytical sense, it was clear that just as electromagnetic waves propagated all frequencies in a vacuum, that was true for gravitational waves as well, and including the UHF band as we are using that name. And so the question arises really, will gravitational wave astronomy evolve in the same way as electromagnetic astronomy has evolved? So here's a picture taking us from 1820. I don't quite remember 1820, but nonetheless, into the 1930s with Grotreber and Jansky and people developing radio telescopes. Then immediately post-war with rockets going up to bring X-ray detectors to bear on astronomy, and then satellites into the infrared, and finally into the gamma rays and gamma ray bursts and so forth. So the development of electromagnetic astronomy has been absolutely fantastic, reaching new bands all the time. And so are we going to follow exactly that path? Well, maybe not. Gravitational astronomy is not the same as electromagnetic astronomy. There's no scattering or absorption for gravitational waves. So we may have privileged access to the very early moments in the universe in a way that electromagnetic astronomy doesn't have. So it would be no surprise if in the end we have a big focus in this frequency band on cosmological signals. Gravitational waves, as you know, are emitted by acceleration of large masses. So UHF sources, because of the short wavelength, will require extremely high densities, and we don't know whether those actually exist in nature yet. On the other hand, since gravitational waves are a distortion of space-time geometry, so they may allow us to explore the geometry of the universe, including higher dimensions and things like that. So that's an exciting prospect in front of us. I guess we're all familiar with pictures like this showing from frequencies 10 to minus 9 up to sort of 10 to the 4, and rather begrudgingly up to frequencies like 10 to the 6. And we've got to get used to, and I think the whole community has got to gradually get used to the fact that actually frequencies higher than this exist and will be of interest. So here's a nice purple area for us to explore above the frequency range of LIGO and Virgo. And it's interesting that some of these little black squiggles are upper limits. We already have upper limits in some of these frequency bands at ultra high frequency. So a start has been made. So what has this group, the UHF-GW group, achieved so far? Well, as you've heard from Fernando, after the first workshop, we generated I think a quite impressive document, over 50 pages long, and that is now a living review in relativity, and the archive number is given there, and that is a very substantial statement of the scientific case for working at very high frequencies, and I would say the technical resources that are scattered around us, but we haven't quite yet brought to bear on the problems. The group has carried out an audit of interested groups in the UHF via a questionnaire. I'll come back to the results of that in a moment. We've held discussions with the Gravitational Wave International Committee about possible interfaces and how we might work with them, and that discussion is still in play. So this workshop will form part of developing our strategy for how we should interact on the international level. And we've organized the workshop starting today. Here's a picture of the website that I mentioned when I gave thanks to the Stephen Hawking Centre, and there is a lot of detail there for people to look at and sign up to advance this area of science. Well, the questionnaire was very interesting. We haven't really completely analysed it yet, but here are some of the headline results. 6 experimental groups responded, and 25 theory groups responded. So that tells us something, doesn't it, that the theorists are engaged in this quite a bit. The total staff effort recorded was 73, presumably not full-time, but nonetheless, that's a not insignificant number of people interested in this particular area of the frequency band. The effort was spread among 17 countries. I think that is quite an interesting figure, because if you go onto the LIGO website, you'll see that their membership involves 19 countries. So not so very different from us, in fact. So we may feel ourselves an international committee looking after UHF-GW matters. There were several experimental areas which didn't respond to the questionnaire. Perhaps they hadn't heard about it, and we will try and contact them and encourage them to join up, because it's very useful to have these statistics to understand what's going on. So I do really encourage people to join the Google group, which is available from the website I've shown you, and stay up to date with some of these initiatives that are being made. So the questions that we're facing, Fernando mentioned this right at the beginning, were, which technology should we develop? And I'm not expecting you to read this slide, but this was a list of technologies produced actually within the European Space Agency when they were choosing the technology to use for LISA. And the only thing you need to know about it is that there are a lot of different technologies available. So we're not starved for a choice in that respect. And going on to the science case for working in the UHF, again, don't in a sense look at all the detail, but if you take discrete sources, neutron stars, primordial black holes and things like that, compact objects, there's a lot of activity in this frequency range between, say, 10 to the 4 and 10 to the 18 hertz, illustrated in this, which is a graph taken from from the Living Review article. And if you put aside discrete sources, then cosmologically, again, there are a lot of cosmological theories which predict radiation in the wavelength band we're talking about. Unfortunately, in this case, of course, they're bounded by the nuclear synthesis limit, and that is going to set us quite a technical challenge. So there's a lot of technologies, there's a lot of science, both discrete and stochastic, and we really need to formulate some kind of strategy as to where we maneuver to make the best progress. This needs discussion, and I urge people to remember that we've got discussion groups set up in this workshop for exactly that reason, so that people can discuss. And here are the topics. Today, prospects for tabletop scale experiments. Tomorrow, theory development of UHF-GW science. Thursday, prospects for large scale experiments. And on Friday, a more diffuse topic, if you will, which is the future of this initiative, and what we should be doing and how we should be doing it. Can I just remind people that the chat line for asynchronous discussion is the Mattermost chat line, and that's available too on the workshop website. So I sort of sat back the other day and thought, well, what should I be looking for at this workshop when listening to the talks? And there were two kind of slightly technical issues. One is that we must remember, given that I think some of the importance here is going to be cosmological, we must remember that if you're going to have a credible result from a gravitational wave detector detecting a cosmological background, you must be able to differentiate between a random signal and random noise. And that is tricky, and it needs a different style of operation or a different style of detector. So we must bear that in mind. It's no good just getting the sensitivity for a cosmological signal. You need to be able to differentiate between a random signal and random noise in a way that convinces your peers. And the second issue that I'd be looking out for is that some of the detector ideas that are being proposed are quite complex. And just suppose, I'm not criticizing anybody here, but just suppose that in this complex theory there's a flaw. Of course, in other branches of astronomy, you'd have a laboratory source of your radiation that you could just switch on to your prototype detector, and if it didn't work, you would scratch your head and go away and think again. We don't have that luxury. We don't have laboratory sources of gravitational waves at the moment, and probably never. And so we have to be very careful in the theoretical basis for our detectors, that it's completely secure before we start saying to somebody, I didn't get a signal, and so there are these cosmological or astronomical conclusions that we should draw from it. It's a subtle issue, but it's penetratingly difficult in our frequency range and in this science to proceed without a lab source to stimulate detectors. There are a couple of other things that we might want to think about, more to do with the organization. First of all, I've shown a picture here of the LIGO scientific collaboration, which I think is something like 115 or 120 different institutes. Is our area of science going to be that complicated? Are we going to have 100 and odd different institutes interacting, or is it going to be much smaller collaborations of just a few groups together in certain areas? Is the nature of our experiments going to be different from LIGO and Virgo? Are we almost always going to be talking about kind of lab scale experiments, like the picture at the bottom, compared to kilometers the size of LIGO and Virgo? So those will play a part, I think, in how the UHF-GW initiative evolves in the future, and that's the subject that we will come back to for the discussion on Friday. You could say it's the question of how should we organize ourselves to maximize our rate of progress, and we've got to take into account our own particular requirements and our own particular characteristics. So is gravitational wave astronomy going to look a bit like electromagnetic astronomy, but not quite. So we're going to see some timeline like this, going from advanced LIGO to we don't know when. And there are some missions and experiments that we can see along the way. Pulsar timing, LISA, LIGHTBIRD, the Einstein telescope. But then intervening in this timeline, will there be UHF-GW measurements being made that will emulate the rich spectrum of astronomy that is being done using electromagnetic waves? We don't know. But anyway, thanks for listening. And now for what I think is going to be a really interesting workshop on UHF gravitational waves.
Perfect. Okay, thank you very much, Mike. I really appreciate it. It's a very nice presentation, and it's a good way to start the workshop. I think, and you had a good timing also. I can see Juan is raising his hand, so maybe we can give a chance to Juan to say something before we continue. Juan?
Thank you, Fernando. Thank you, Mike, also for a beautiful talk. I have a question with respect to the limits from Big Bang nucleosynthesis. You are assuming that somehow the sources which will give rise to this stochastic background originated before Big Bang nucleosynthesis. But if you think of events like primordial black holes colliding and generating a background of stochastic gravitational waves after recombination, after they start merging, then you would generate a background that can be as large or much bigger than the stochastic background from Big Bang nucleosynthesis, and you will not have such a constraint on you. So I think we should be more open to the possibility that there are backgrounds coming from specific sources. I'm not saying any source, but very specific sources which arrive at megahertz to gigahertz above the Big Bang nucleosynthesis bounds. Just a word of caution.
Yeah. Hi, Juan. Great to see you. I agree with you absolutely entirely. We're going into a totally unexplored area, and we should be completely open-minded about it. On the other hand, we've got to at least tip our hats towards the known structures in cosmology and astrophysics, if only for reasons of kind of credibility amongst our peers. But no, we should absolutely be completely open-minded. And thank you for reminding us of that.
Okay, well, thank you, Juan, and thank you, Mike, for the response. So now I think we can move quickly, and Francesco will take over now with some announcements and introducing the next session.
Yeah, let me just